So first, a few words about Epson as a company. Epson is part of the whole company is called Seiko Epson Corporation. It's a Japanese company with around about 10 billion euros turnover worldwide. The majority of business is for printing solutions, so printers, where you probably have heard the name Epson already as well. Then part is video projectors, and then there is this manufacturing and wearable related products, and that's where the micro components are in. So the speciality about Epson is that we are doing many things within our company. As you saw before, Epson has the consumer products, printers, projectors, and in order to support that businesses, we are doing our own semiconductors and timing devices, and Epson does as well robots, for example. So we have very high level of vertical integration, and our timing devices, like the ones we talked today about, so programmable oscillators, we are using our own semiconductors. We design, we manufacture them in-house, so we are not a fabless company. We manufacture the raw material for the crystals, for the timing devices, the timing device itself, and we bring the semiconductor and the crystal together into oscillators. And we then use for the production, for the assembly, our own Epson robots, and then of course finally testing and shipping to customers. To get started with the programmable oscillators, we need to first talk a little bit about the basic oscillation topics. So here we talk about megahertz oscillators, and the basis for that is a crystal chip, a crystal blank, made of quartz material, which is temperature stable, more temperature stable than other parts. And this crystal blank is cut out of a block of raw crystal material in a so-called AT cut, and that causes this device to oscillate in a so-called shear mode. So the surface, the top and the lower surface oscillate shear against each other. And oscillation frequency determining is the thickness of that crystal blank. So as slimmer this crystal gets, as higher the frequency it supports. In order to get this crystal blank to oscillate, there is energy needed. This energy needs to come from a semiconductor, because the crystal is a purely passive piezoelectric material-based crystal blank. And this oscillation circuit inside an IC has to fulfill certain requirements to deliver enough energy to excite the oscillation, but that's not the topic for today. At the end, oscillators are constructed nowadays having a ceramic package as a base. Then the semiconductor is assembled in there, be it with wire bond connections or via flip chip bonding. And then on top of that, a crystal blank is glued into this package. Finally, there is a lid, so a cover on top of this ceramic package, and this whole thing is vacuumized in order to lower the loss of the oscillation and therefore lower the electrical current required to excite this oscillation. One important parameter in that context is that even I have a certain frequency, let's say a 26 megahertz oscillation, not every single oscillation cycle has exactly this 26 megahertz on frequency. So there are parts, oscillation swings, which are a little bit faster and others which are a little bit slower. And this can be looked into two different ways. One is if I use, for example, an oscilloscope, I see that this whole thing jitters a little bit. So therefore, if we look at this fact at the time base, then we talk about a jitter performance. Jitter performance is a specification important for example, networking applications where the clock is actually causing some read of data or whatever. For other applications, like in RF communication, customers, people talk about something called phase noise. Or if we look at this in a graph, we have here the intensity over the frequency. So we see most of the energy is at, in my example, 26 megahertz, and the chance, the energy that another frequency happens is a little bit lower. So this is basically the same thing here. This is how this jitter looks in the time base. This is how the phase noise, the jitter, is appearing in a frequency-based system. Frequency-based, so phase jitter performance, is something which typically is discussed in RF communications, as mentioned. One further thing, just for the sake of completeness, megahertz crystals have a temperature characteristics which have that sort of shape, so this S curve over the temperature. Now, going into the topic of today, there are different variants of oscillators available, and I think it's important to understand them and to understand what's their pros and cons. So there are kilohertz oscillators, which are out of scope today, but just for the completeness, they are in the slide. Then there are regular called AT-cut crystals and oscillators, or crystal-based oscillators. That means there is a conventional crystal blank inside. This regular SPXOs, so single packaged oscillators using this AT-cut crystal, have frequency limits. So typically they are maximum up to 75 or 60, depending on the size of the part, megahertz, because as mentioned before, as faster the oscillation is, so as higher the frequency, as slimmer the crystal blank gets. So at some point the crystal blank is starting to get fragile and can easily break. So therefore there is a certain physical limit till which the device itself is mechanically stable enough to be produced and used by customers. Conventionally, then, if you want to go to higher frequencies, in the past there was possibilities to use special types called overtone crystals. So you excite this oscillation not in the fundamental mode, but at the third overtone, for example. But that excitement, that mode, is not so good, so it's not so widely used. And for higher frequencies, typically so-called SAW, surface acoustic wave technology, was used. That means the structure of the device is different, partially as well the material it's used is not quartz anymore, but it's some synthetic material very often. And they have frequency limits of 50 to 700 megahertz. Nevertheless, they are relatively expensive to produce because they need relatively large chip space. So they are price-wise not so competitive. And for that reason, other technologies have evolved. And we as Epson, we are phasing out this SAW technology pretty much because we replace it with other things. Another option what's possible is, as well since many years, is to use a regular megahertz oscillator like this. But then add a PLL, so a phase lock loop, which allows to multiply the oscillation frequencies, and then again you can reach higher frequencies. So similar to SAW technology. The drawback of that, however, is that due to the fact that a PLL, so a phase lock loop, a regulated loop, is used, that means that the jitter performance is getting worse. So you have more jitter or phase noise, depending, as I said, if you talk in the time or in the frequency domain. And therefore, these parts have had some certain limitation in the past. Nevertheless, PLL technologies are getting better continuously. So that is the reason why SAW technology is not so relevant anymore nowadays. And then one additional, and this is the main topic for today, one additional technology is to use a PLL type oscillator, but not, so unlike this version here, where the PLL is factory fixed, so it's having a fixed multiplication factor and so on. Programmable SPXOs allow flexibly to change the frequency the device should output. So they can be programmed to output the frequency and potentially, sometimes in our case at least, as well certain features, temperature range and accuracies and so on. A very special technology which Epson has developed is called HFF technology, so high frequency fundamental. With that, we reach significantly higher frequencies, and that's the reason why Epson is phasing out SAW technology, because even for very low jitter applications, so for high-end stratum 3, whatever sort of network systems, we have very low jitter devices with our HFF technology. What we do there is we are using photolithographic processes to manufacture our crystals. All below 2.5 by 2.0 millimeters are using this process. And when using this, we have the possibility to make not the complete crystal blank slim to the extent needed to reach the frequency, but we have only a certain part, like shown here, made slimmer, and the rest of the crystal blank remains thicker and therefore has increased mechanical stability. And with that sort of technology, we can go up to 500 megahertz right now. We're working to bring this further up, so therefore we reach levels where historically you could only use PLL type technologies or SAW-based oscillators. Reason why we are focusing very much on programmable SPXOs as well is that, as mentioned before, for a fixed frequency oscillator, the thickness of the crystal blank determines the frequency. And that means if I want to offer 20 frequencies, I need to have 20 different crystal blank designs. And each crystal blank, there are many characteristics like frequency dips and so on. So there are many things which need to be considered when designing a crystal blank and optimizing it. So it's really quite extensive process, as well costing money, of course. So therefore, if I want to have 20 different frequencies covered with a fixed frequency, I need 20 of that specific crystal blank designs, and that for each single series. So that's quite some effort, quite some money, and especially taking quite some time. And for that reason, we focus on standard frequencies. So typically we have standard frequencies, a number of 20 standard frequencies, covering, I would say, 95% of the demand. And then, so for the high volumes, and then for the rest, we use programmable oscillators. But as well, these things here, so these frequencies can, of course, be covered with programmable devices. And then we have, as said, the possibility either the fixed programming inside or really programmable from outside. Programmable from outside means there is a programmer which the customer can order, which our distributors like Ineltek have, which we have. So there is a possibility to program a blank. So our factory produces the blanks, and then either in the outgoing inspection at our factory or at the distributor or yourself, you can program this device. So there is a one-time programmable memory inside. So you can, with that programming tool, you can define certain parameters of this phase lock loop so that this programmable oscillator oscillates at the desired frequency and the desired accuracy. The advantage of this technology is that in the conventional crystal production, you need to produce the crystal, and I said before, we have an AT cut, so you cut certain crystal wafers out of a crystal block, and that crystal wafer needs to be processed, needs to be brought to the thickness required to define and to have that frequency. You need to sputter electrodes on it and so on. So this is a process taking at least 2 months till you have the crystal blank ready. And then finally, you need to put this together with an IC into a package, final inspection and ship. So the overall lead time of a fixed frequency oscillator is in the range of 3 months. And by offering these programmable oscillators, we can of course pre-produce the crystal blank. we can pre-produce the oscillator. So we have a final product available, which just needs to go into final inspection, at which the PLL parameters are programmed onto this device, so we can shorten that lead time and we can make sure and guarantee that parts leave within 2 weeks after ordering, rather than 3 months for a regular oscillator. So we can be far more flexible and faster in shipping goods. An additional advantage, of course, is since these parts are programmable, they can be pre-produced in really high volumes. So that means we have a large stock of these crystal blanks or oscillator blanks available in our factory. So therefore, the capacity is very, very high, which we can ship within 2 weeks. Here with my last slides, I want to show a little bit the different types of oscillators. So this is just for the completeness, showing the differential output oscillators. That's oscillators which are typically used in network applications in order to lower the jitter performance in the system, in order to lower the environmental impact, EMI, and so on. These parts in networking applications very often use differential output rather than a CMOS single-ended output type oscillators. And you see these jitter types in the range of 50 femtoseconds, 300 femtoseconds. When we go to CMOS PLL, we have this product portfolio. So down here you see the size of the devices, you see the name of the series, and you see the specifications, you see the temperature range. So we do have fundamental, so fixed frequency oscillators over here, and we have PLL type oscillators down here, and green marked are our main promotion products. So you see we have products for all different temperature ranges going up to 125 degrees C. Of course, the frequency output range is very high, while for the fundamental parts we have the standard frequencies mentioned before. Here a little bit the details of the latest programmable oscillator types. So you see as well the jitter here 50 picoseconds, while we had, if you recall 2 slides earlier, this differential output HFF type oscillators had like a factor 1000 better jitter performance. So jitter definitely of programmable types are worse than for networking HFF type, but they are very competitive and quite good performance for regular video processing and so on, with the advantage, as said, very quick availability and easy to have blanks stored anywhere in the supply chain. As mentioned before, the jitter or phase noise, so this is now in the frequency domain, so it's phase noise. The phase noise of our newer series like 8201, that's the blue line, is improved to the previous version 8101. So we're continuously working on improvements of these phase noise or jitter performance so that the gap to a fixed frequency oscillator is reducing. And for that reason, we see this is a very useful product, especially for smaller volumes, especially for special frequencies, which otherwise manufacturers like us may hesitate to make an optimized crystal blank for. Finally, the last slides, actually, I want to show very quickly a very special version of that programmable devices, so-called spread spectrum oscillators. More applications see problems with the EMI emission, so with the EMI performance in the system. Here, generally, as lower the jitter or phase noise of the oscillator, as stronger, as larger the EMI emission peak at the nominal frequency is, like in my previous example, 26 megahertz. So a PLL type oscillator may give some relaxation over a fixed frequency here because of the slightly larger jitter performance. The EMI emission peak is spread over a wider frequency range, so the emission peak is lower. But if that is not sufficient, there is a very specific type of programmable device called spread spectrum oscillators, which actually allow to modulate the frequency, the output frequency. So you intentionally not keep the 26 megahertz, but you're changing it. And by doing this, you are bringing the EMI emission peaks down, and you're spreading the EMI emission into a wider frequency range. And here we have different spread types. So this is what the emission spectrum could look like. So in case of a fixed frequency, that's this light blue line where the emission is very limited frequency, but higher peak. And for a spread spectrum, we intentionally modulate, we change the frequency over time. So like shown down here in the red graphs, so we modulate, we change the frequency following a certain modulation scheme. In this case, it's this sawtooth, and with that we widen the emission spectrum, but we bring the peak down. So these are devices which are widely used in applications like video processing, because video processors require quite some power, and therefore they have a relatively large EMI emission, and for that reason that sort of application, but many others, benefit from a spread spectrum oscillator.